I'm Ted and welcome to my AINT308 Assignment 2 Task 6 demo. Now this is going to be a long one because there's quite a lot in it, but I'm going to be discussing what I've done for my mini project in my University of Plymouth AINT308 module for Task 6. So in this task we were asked to come up with a mini project we can complete using OpenCV and computer vision. Being a robotics engineer, I tend to deal with a lot of resistors, and once I've been tinkering and breadboarding, I normally have a fairly substantial pile of resistors left over that I don't really want to sort through. So I aim to use computer vision to make an algorithm to detect and give me the value back of resistors, which turned out to be more complicated than it seemed. So what I'm going to do is I'm going to step through each part of the final algorithm, I guess you could call it, my final process of how to detect the value of each resistor. So in the first step, I get a source image. I did want to use a webcam feed initially to get the images, but I found that the webcam I had was too noisy and presented a couple of optical problems, and lighting wasn't consistent, shadows made it really hard to read resistor values. And so I made this. So this is a webcam, it's been cannibalized, put up in the top, and a little stand with LEDs to try and get the lighting all Gucci. Unfortunately, even this couldn't save the webcam. It's still noisy and the colours bleach out, so there's no distinction between colours, and that's a problem because I need to be able to detect the differences between colours. So instead I'm going to use stock images. That's what I've developed my code for. So in the first step we load in the image. In the second step we want to try and begin isolating the bodies of these resistors so that we can start to do some analysis on them. So a nice way to remove the background is to turn the image into HSV color space, and then I'm going to use the luminance channel, or the value channel, which shows how white or black a pixel is, to get rid of the white background. So here we can see this is a simple threshold on the background. Anything that is less than a certain percentage of white becomes black. So you remove the background and we can begin to see where it's beginning to isolate our two resistors in the image. It is quite a noisy image though, there's quite a lot of holes and we don't want the stray ends of the resistors to impact the algorithm. So we're going to take it a step further and we're going to erode the entire image. So around every single blob we're going to take away a few pixels as if we're chiseling it in from the outside. And that's going to get rid of all those little extraneous pixels and the thin ends we can see. But now we're left with a bunch of holes. Not to worry. We're going to dilate the whole thing again, so instead of coming out from the inside and coming in, we're going to go from the inside and build out to get rid of those holes. And finally, we're going to go back outside, in once more, and now we're left with a nice mask for the two resistors, which is more or less the shape of the resistor. There is a bit of tolerance because we can deal with the bands across the entire resistor, so if you miss the top or the bottom, it's not a big problem. So now we've got this nice mask, we need to separate the two resistors. So to do this, we're using the OpenCV simple blob detector, and we're detecting those two big nice blobs, extracting their features. So here we can see we find the contour of those blobs, so the outer line, so we know that the resistor is going to be within that area. The next step is reasonably simple. We get a rectangle and we keep shrinking it until it fits around that contour, the smallest it can be. It might be a little bit rotated. In this image, they're horizontal. The code will actually, if it's a rotated resistor, it will rectify it and rotate it to be horizontal in the next step. So we use that rectangle we've just shrunk down, that bounding box, and we use that to crop each resistor into a separate image, as we can see here. So now we've nicely managed to go from having our two resistors in the one image to exclusively the body of each resistor. Pardon me. But we're far from done yet. What we need to do next is we still have background, the white background in these resistors, and we're not going to want that background because if we start taking any averages, that white will change our average and corrupt our colour. So again, going to do a threshold on the luminance channel or the value channel to get ourselves a nice body. Again, has a couple of holes in. This time though, we're not going to get rid of those holes because when we look at the resistors, we see that those holes are actually where those reflections of the bright lights on the original stock image are. And we do want to get rid of those because those reflections will falsely indicate an area as white, which will again make the average value that we're going to get from that range wrong. So by getting rid of those white hotspots, we get a more consistent colour reading for each of our colour bands. Now the next step is where it gets a little bit heavy. In order to separate those bands out, we're going to want to filter out the colours. A more crude approach would be to convert it into one colour space and do thresholding on that. However, in order to achieve better reliability and avoid getting false readings on different bands, and sometimes if you take a yellow band for example on this first resistor, the yellow is very close to the beige of the background resistor, and so it's possible for a thresholding mechanism to consider them the same colour and then we miss a band. So to avoid this, we convert each resistor into 4 colour spaces. Now it's easier to see here, going from the top to bottom, we have, I believe it's YCRCB colour space, HSV, lab, and then RGB. It's easy to see that some of the bands are very faint on some of the images, and if you split those further into individual channels, sometimes the bands disappear altogether. Because we have so many colour spaces, it's now possible to threshold each colour space, and then where they correspond, we can say, right, that's definitely a band. So in the code, the next step will split each of those 4 colour space images for each resistor into 3 channels, and threshold each channel to give a total of 12 thresholded images for each resistor. Once we have those 12 images, we can go over each image, and everywhere a column lines up between 2 pictures, we count that. If there are more than 2 columns that line up between 2 pictures, so if we have 3 or more images in which there are white bands, we know there's probably a band there. And by marking that in a overall band mask, we can produce these 2 masks, which, clear as day, show where the bands on the resistors are. So we can now use this mask to find our colours. So the next step, we go across this mask. If it's white, we take the corresponding area in the cropped resistor image up at the top there, and we average out all the pixels. But we do ignore pixels that aren't in that body mask that we created. So the second picture from the top of this column, we get rid of those pixels marked as black. That way we get rid of the background and we get rid of the highlights. Once we've found the average, we can mark them out. So we have a lovely resultant image here. Pink is not a colour on a resistor, so because you can't mark it black, because black is a colour on a resistor, we're going to mark it pink to show that this isn't a band. And we can clearly see that each band has been nicely matched to the nearest colour in the dictionary. Once we have these colours all categorised in the dictionary, it's very straightforward to put them into an actual value. So we go through a really big switch case statement, depending on how many bands we've detected, which band we're currently looking at, what colour the band is, and which direction we're reading from. In order to get the direction we're reading from, you can see that with the bands, all of the bands are the same distance apart from 2 at one of the ends. On the resistor on the left, we can see that the gap between the yellow and copper bands on the far right is much bigger than the other two gaps. And on the resistor on the right, we can see that the gap between the first and second bands is bigger than the other 3 gaps between the other 4 bands. The end with the bigger gap is the end we read from. So on the resistor on the left, we read from the right, and on the resistor on the right, we read from the left. I know it's a little bit topsy-turvy, but that's the way it turned out. And once we have all this information, we can run it through a nice big switch case statement to end up with our output. And we can use those bounding boxes from earlier, just above my head. This one here. We use this one, and we print the text on top of that box, on top of our source image. And there we go, we've identified our resistors. That's quite a lot to identify resistors, and there are definitely improvements to be made. But I hope you enjoyed this short demonstration, and I hope you stay safe through the rest of this quite grisly pandemic. So, see you next time.